did with Dr. Villavarius several months ago. It's just on the formation of the galactic warps through galactic flybys. Without further ado, I'd like to start off just by talking about a little outline. I'll start y'all off where I kind of started off, which is just basically we'll talk about galaxy classification, work our way into spiral galaxies, and then we'll talk about warps after that. After that, we can get into simulations, the types of simulations that we used, and the differences in the simulations that we used. And then we'll get some really nice data from that as results, and then compare them to some data that we actually have seen from rigs. So we can start off with talking about galaxy classification. There's two main types of galaxies, which are the elliptical galaxies and your spiral galaxies. Your elliptical galaxies are just comprised of stars modeled in a spherical shape. And then your spiral galaxies are just notably defined by their spiral structure. And this right here was made by Edwin Hubble. It's his own tuning fork. He made this in about 1926, I believe. But yeah. Spiral galaxies. So there's three main parts to a spiral galaxy, which is basically just the disk, which is, the thickness of it is very, very, very small compared to the actual diameter itself. It's about 1/100th of the size. At the center of our disk, we have our halo, which is a spheroidal component, mostly comprised of old stars. And surrounding the two is a large dark matter halo. Well, this dark matter halo is extremely important to the structure of the galaxy, and it also plays a very vital role on the rotational velocity of stars. As you move farther out into the galaxy, we see less stars, but since this rotational velocity is heavily dependent upon the enclosed mass, this dark matter really is the missing mass for that rotational velocity. All right, yeah, so galactic warp. So when you look at a spiral galaxy up in the night sky, we primarily, you're more likely to see it bent out of shape, which is what we define the galactic warp as. It's just that flat structure that's kind of bent out of shape. You can have that weird U shape or this S shape right here. And you can really define the strength of the warp by determining this angle here, alpha. But there are a few different ways that galactic warps are thought to be produced. I just wrote a little list right here of some of those ways. We have the intergalactic magnetic fields acting on the neutral hydrogen gas in the disk. Torques can be exerted by a misaligned halo onto the disk. Distortions in the dark matter halo by a satellite galaxy can also alter the disk. And also cosmic infall might also have a pronounced warp, or might cause a pronounced warp. But the main thing that we're going to be looking at really is just how distortions in the disk can be caused by galactic flybys from satellite galaxies. So we'll talk a little bit about in-body simulations. What are they? So they idealize our initial conditions, which is just modeled by a number of particles that have a distribution that kind of reproduces the mass density of the galaxy. And the code actually calculates a gravitational force and acceleration, and that just kind of integrates the evolution of the system. But right here I have like a really nice color coordinated layout of our what we're doing. So we have our blue particles as our dark matter halo. Our yellow is that bulge right here at the center. We have our disk labeled into white, and then we have that red as our perturber. So here's how we kind of set up the simulation that we ran. Over here on your left-hand side, we have the two initial objects that we're going to be looking at, which is our perturber and our host. And here we have a nice little table of the differences in the simulations that we ran. The only real difference is the inclination of the perturbing galaxy onto the x-axis. And that is fairly the only thing that is different between all of our simulations. As you can see here, our initial distance and our initial velocity relatively stay the same across all of our simulations. But we're pretty much looking at the angular momentum transfer of the disk, or the perturber to the disk. And one really easy way to find your angular momentum is just taking your hand, stick it out to the edge of the disk, and then curl your fingers to the rotation of the disk, and your thumb is going to point in the direction of the angular momentum. All right. When we initially did this, we had a small little problem trying to find the total, or the angular momentum of the whole entire disk. So I'll show you right here how we kind of went around that. So we divided our disk up into many concentric rings, and then we tried to figure out what the deviation off that z-axis that I was just talking about was. And right here, we have a very exaggerated image of what a warp looks like in terms of concentric rings. Like I said, this is heavily exaggerated. You might see something like this in more of like the gas gauge, but you won't see anything like this when we're talking about our stellar components. But each of these rings are pretty much going to tilt slightly more than the last ring previous to it. And then we'll also see that these rings up here in the center don't really change their angle with respect to one another. Now they do kind of change altogether, but not too much. Alrighty. Here's a nice little video. 3 projections. You have one on your YZ, your XZ, and your XY. And at t=1, it just kind of passed. You can see a really nice warp showing up. So when we plot our data from what we just had, we get something that looks like this. So our initial, at t=1, our time of closest approach, we see the initial perturbation, which is that perturbation off of the derivation off of the z-axis, that angle. So we can see it goes from a maximum of 10 for those outer rings, and you can see over there the color coordinated rings. And they'll slowly kind of dampen over time. Your inner rings will kind of like just move up, and they'll get inclined by about 2.5 degrees, and they'll just kind of stay around there. And all the other rings kind of gravitate around that. So I know that sometimes looking at those graphs can be kind of hard, but here I have like a nice little video. So each ring that you see here is just kind of like a deviation of 2 degrees off of that z-axis. And so right there, you can see a little clump of dots together. Each one of those dots represents a ring. And you can kind of see how each line after that represents 2, 4, 6, 8, 10. That's just the amount of degrees that it's being deviated off that z-axis. But one of the nice things that we got out of this is that we were able to look at a paper described by Briggs. He looked at the 21 centimeter hydrogen line and other various galaxies. And he got some shockingly similar results that looked like this. This galaxy, NGC 628, it is in the opposite direction of the galaxies that we were using. However, we see a shockingly similar result, and that is just that the angular momentum is hooked, or the direction is hooking in the direction of rotation of the galaxy. Now, there's a big difference between these two. Like I said, there's one with the hydrogen disk, or the hydrogen, and then there's one with the stellar components. These ones go up to about 20 kiloparsecs of deviation. Ours only go to about 10. All right, so our results. What did we find out, and what did we see? So, yeah, so the inclination of the smaller rings hover around the same angle. But if you go out further, you get more of a warp effect the farther you go out. And the lifetime of these warps really just increases with radial distance. So we saw that small dampening effect happening, and as you go further out, it lasts a lot longer. And the axis of rotation is the same in direction of the angular momentum, but the biggest one that I really want to talk about is how it hooks in the direction of rotation. And that was like a really neat thing that I got to see. You can kind of compare the two, how they are right now. You just have to realize that for ours, it goes into the opposite direction. So just flip this arrow.
Okay, great. Time. So,
thank you.
We have 2 minutes.
Thank you.
So we have 2 minutes for questions.